so that when I add something that's harder than a polynomial, you can do it. Okay, so I want you guys to type that graph into your calculator. Okay. So, not an accurate sketch at all, but you have something in front of you that looks like this. Some sort of min and some sort of up like that. We agree? Everyone agrees? Okay. So, what do the critical numbers of the first derivative give us? We talked about this. What are the critical numbers? So when you set f prime of 0 or f prime of x equal to 0, what do those critical numbers give us? Maxes and mins and points of inflection. So we know that when f prime of x equals 0, we know that makes m tangent equal to 0. Today is your TSN turning point day. If you don't get today, the rest of the unit will be impossible. So we're paying attention today, hence why I pray for self-control. Pray it twice. All right. So m tangent equals 0 is where the horizontal tangents occur. And horizontal tangents occur at maxes and mins and points of inflection. So maximum, minimum, points of inflection. So I am suspicious that I'm going to have how many critical numbers on this graph in the first derivative? 2. Because I have a point of inflection here and I have a minimum there, correct? So I'm suspecting that I'm going to end up with 2 critical numbers in the first derivative. Yes? So let's see if we can algebraically do that. So let's find the first derivative. I like how it boxed the graph. It's like highlighting it. It's actually boxed something correctly for me. Okay. What's the derivative of x to the 4 minus 4x cubed? 4x cubed minus 12x squared. And then what do I do? Set this equal to 0, take out a 4x squared, and I'm left with x minus 3. So my critical numbers are x equals 0 and x equals 3. We agree? 2 critical numbers. I'm suspecting that 0 is going to be my point of inflection based off the fact that I can see a graph in front of my face with the point of inflection at 0, and I'm going to have a minimum at 3. So how do we find that out actually algebraically? Because if your calculator got taken away from you, how would you do that? We make ourselves a number line. Our number line has arrows on the end of each because this graph's domain is XER. The domain we looked at on Friday and on Thursday was a restricted domain, and we got endpoints, correct? Those endpoints could be absolute maxes and mins or endpoints. That was the only option we had. Here, our domain and range carry on for life. We agree? And we put our critical numbers on it. So we have 0 and we have 3. I want to prove that this is a point of inflection. And had I not looked at my graph, I wouldn't know this is a point of inflection. But we're looking backwards, forwards now, just to prove the point, okay? Because we should be able to do this without looking at our calculator, correct? But I know that's going to be a point of inflection, and I know this is going to be a minimum. But how the heck do I show that without cheating and looking at my calculator? Well, we have to discuss what those tangent slopes are doing around the point of inflection and the min or max, correct? Now, the key thing is when you have a point of inflection, your graph is either decreasing to decreasing, or it's doing what? Increasing to increasing. If it's a minimum, what's it have to do? Decrease to increase. What's max have to do? Increase to decrease. He's mocking my D keys that I said first. Sorry, messed up. Jeez. Can't be perfect all the time. All right, so let's look at this one and see what it's doing. For this point of inflection, what is it doing on both sides? Decreasing to decreasing. And how do you know it's decreasing with the tangent slope? Because as it decreases, my tangent slope at all of these spots will be what? They're decreasing. So if I pick this point and I plugged it into the first derivative, it's going to give me a negative slope. If I plug this x coordinate in, it's going to give me a negative slope. If I plug this x coordinate in, it's going to give me a negative slope. What about this one? Negative slope. And this one would give me a negative slope. And this point would give me a negative slope, correct? Do you see that? So we have to run test points of values on opposite sides of our critical number. So I run f prime of x test points, and I run them along the top, okay? So this is the equation for f prime of x, this one right here, without taking out the GCFs. Do you see that? But all we really need is the sign, not the actual slope. So this point is, this equation, where I take it out, is actually easier to plug into. So I need to pick a test value that runs between 0 and negative infinity. What do I want to pick? Negative 1 is probably the easiest one to pick. You could pick negative 0.7653, but why are you doing that? Stop the madness. Like, pick something else. Okay? So we have to plug it into this formula. So we're going to get 4 times, I don't know why I'm taking a sign there. It's just here. So we go 4 times negative 1 squared, and then negative 1 minus 3. So I'm going to get 4 times 1 times negative 4. And what do I end up with? A positive or negative number? Negative. So when I plug in negative 1, I get a negative here. What does a negative mean when you plug it into the first derivative? It's a negative tangent slope. And how do you get a negative tangent slope when the graph is doing what? Decreasing. No, this is going to stay for life. Decreasing. So we know where f prime of x is less than 0, the graph is decreasing. And where f prime of x is greater than 0, it is increasing. So now we have to run a test point between 0 and 3. What do we want to pick between 0 and 3? What value? I would pick 1, you could pick 2, you could pick 2.5, you could pick 1.5, you could pick 1.333 repeating 4/3 if you're a rebel. I'm not. I'm like, hey, what's the easiest? 1. That's what I'm using. So I'm going to use 1 here, and I'm going to go 4 times 1 squared, bracket 1 minus 3. So I get 4 times 1 times negative 2. And so what does that result in? A negative number, so it is decrease. And what are we hoping? Oh my gosh, it's getting worse. I need a nap. I'm just gonna let Katie look at me. So I feel like hoping. What are we hoping is going to happen on the right-hand side of 3? I'm hoping it's going to increase. Yes, I am hoping it's going to increase. So what can I pick? What number? 4. 4. Okay, so I have 4, and then I have 4 squared, and then I have 4 minus 3. Now, unless I want the coordinate on the first derivative, I actually don't have to figure these out. I can go 4 is positive, 4 squared is positive, 4 times negative 3 is, 4 minus, that looks like a tie. 4 minus 3 is positive. What's a positive times a positive times a positive? Positive. So I only have to actually figure out what this number is if they want a coordinate on the first derivative, correct? If not, I just want to know what the sign is. So plus, 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 so it's increasing. So if it asks for the intervals of increase, decrease, we have them. Intervals of increase is from what to what? What's it increasing from? 3 to infinity. And we use round brackets because it's not increasing on 3. 3 is actually a minimum, right? Intervals of decrease are from what to what? A lot of people will tell me from negative infinity to 3, and on a test sometimes it'll say that, but really it's increasing from negative infinity to 3 or 3 to infinity, because that's a lie. 0. Grab a mitt, girl. Get in the game. It's a rough day. 0 or 0 to 3. Because technically at 0 it's not increasing or decreasing, it's a point of inflection. Now, we know that it's a point of inflection whenever it decreases to decreases or increases to increases. But we also have to actually know something about the graph. Sometimes people will tell me it's a point of inflection, it decreased to decrease. But that number is actually an asymptote because it's a rational function and it's in the denominator, right? So you actually have to look at the graph and say, hey, decrease to decrease could be an asymptote. Like it could decrease and then decrease on both sides, right? Then there could be an asymptote there. How do you know there's an asymptote? Well, you would look at the original graph and there would be a variable in the denominator, correct? So there would be a problem there. So just if it decreases to decrease and increase to increase isn't enough information to say that that's a point of inflection. This one's a point of inflection because the domain of this graph is XER. It's a polynomial, correct? So if this graph is continuous everywhere, which it is, if it's decreasing to decreasing, that forms a point of inflection. So that's why we know that that's a point of inflection and not an asymptote, because it's a polynomial function. Okay? And we know that this one's a minimum because this is decreasing to decreasing, and this is decreasing to increasing, so I know I have a minimum there. Correct? So they might ask us what is the value of the point of inflection or minimum. So the point of inflection, a lot of people will tell me, is 0. It has the word point in it. That's a hint that you're wrong. Point of inflection. 0 and something. How do I figure out the something? Why am I plugging it into the original? Because you're looking at the graph of the original. You're pulling a point of inflection off of the original graph, so we have to find it off the original. So we plug it into f of 0. I don't know. X to the 4 minus 4x cubed. So 0 to the 4 minus 4 times 0 cubed, which is 0, 0. Shocking. It was 0, 0, right? That confirms it for us, which is a good thing. You can't be like, because the graph shows it. It doesn't work. Because that's why the AP test is half calculator, half not calculator. Because this will be on the non-calculator. Okay? And then we need our minimum. It's at 3 at some random number that is very low, it looks like on our calculator. So we have to find f of 3. So we're going to get 3 to the 4 minus 4 times 3 cubed. Okay, quiet please. And I get negative 27. So my minimum coordinate is at 3 and negative 27. Right? Does that kind of make sense? We're talking about the graphs of these, the original, the first derivative and second derivative later this week, but if you understand this well, the graphs aren't so bad. So, what did we talk about? We talked about the critical numbers will get us where the point of inflection, max and mins are, correct? We're only doing polynomials today, so it's for sure going to be that, because you can't have asymptotes on a polynomial. Then we take those critical numbers and we make a number line. Wherever the heck you plug in your value in your interval, if it comes out as a negative in the first derivative, the graph is decreasing there because it would have negative tangent slopes. And wherever you plug it in and it's positive, it's increasing because you have positive tangent slopes, right? When you go from a decrease to increase, you get a min. When you go from an increase to decrease, you get a max, right? That's all this is, over and over and over. Okay, let's try another. Should put example 1 on the first one. Example 2. So let's try 2x cubed minus 6x squared plus 6x minus 3. So this is a cubic function. Cubic functions have a domain of what? What's my domain? Always interval notation because we're in calc. Negative infinity, positive infinity. Yes. So we know when the domain is from negative infinity to positive infinity. If we decrease to decrease or increase to increase, it's a point of inflection. Guaranteed. Okay? So we need to get our first derivative and find our critical numbers. So go do that. First derivative, critical number. Our first job is to get the derivative. So we're going to get 6x squared minus 6x plus 6. Set it equal to 0. I get a 6 out front. X squared minus x plus 1. That something is wrong. One of these things just ain't like the others. One of these things just doesn't belong. There we go. Okay. So some people think that when you take a GCF of a 6 out or whatever, it doesn't matter because we're going to multiply by a positive 6, correct? True, unless you GCF out a negative, and then you're going to multiply by negative 1, which makes a difference. So you always have to include this when you do your number line. So we're going to get 6, and then x minus 1, x minus 1. Okay? Please put the markers down. They're distracting me for all of both. So the critical number, sometimes they just ask for the critical numbers. Well, there's only one. It's x equals 0. Sometimes that's the question. Sometimes it's literally what are the critical numbers of the first derivative. Okay? Pardon? All right. Then we have our number line. It is from negative infinity to positive infinity because it's a polynomial and we have a 1. Then we have to run test points. So I'm going to run 0 and 2. So f prime of 0 equals 6, 0 minus 1, 0 minus 1. So what are we going to get? 6. So a positive, correct? Now, guys, if we want to actually get the number, we get 6. 0, 6 is a coordinate where? 0, 6 is a coordinate where? What did I fill it into? Prime, the first derivative, correct? So 0, 6 is a coordinate on the what? On m tangent, on the first derivative graph, right? If you plug 0 into the first derivative and you get a 6 out, you literally just plugged it into the first derivative, so it's a first derivative graph coordinate, right? If you plug it into the original f of 0, then you're finding a point on the original graph, right? Okay? So this is positive. So it is doing what here? Increasing. Because it is a cubic function, we know lots of things about cubic functions. Cubic functions have a max and a min, or just a point of inflection. We agree? Yes. So this for suspicious is a what? Point of inflection or a max and a min? One value. What does it have to be? Point of inflection, correct? If it's cubic, you either get a point of inflection, so one critical number, or a max and a min, two critical numbers, correct? I got one, so I think it's the point of inflection in order for it to be a cubic graph. Put those down or I'm going to be so sad. All right. And then this one, f prime of 2, you get 6. 2 minus 1, 2 minus 1. So you would actually get 6. So 2, 6 is another coordinate, but it's positive. So it's increasing. So this is a point of inflection. And we know our intervals of increase, decrease, there aren't any. Intervals of increase are negative infinity to 1, 1, or 1 to infinity. Guys, stop. And then the point of inflection, how do I find it? Plug it into the original, so f of 1. So I get 2 times 1 cubed minus 6 times 1 squared plus 6 times 1 plus 3. Is that 5? 1, 5? Put it away. 6 cancels, and then 2 plus 3 is 5. Where is the minus from the formula? Keep erasing. So I want the domain always. You have to give me the domain always right away when you do the function. But I want the domain. I want the critical numbers. I want increasing, decreasing intervals. And I want max, min, points of inflection. I want all the things. So this one has a domain of negative infinity to positive infinity because it is quintic. F prime of x equals 5x4 plus 5x squared. Okay, guys, stop talking. Take out an x squared and a 15. And we're left with x squared plus 1. This one you have x squared equals 0. X equals plus or minus root 0, which is just 0. This one we'd have x squared plus 1 equals 0. X squared equals negative 1. Square root of a negative. What happens? No solution. So our only critical number is x equals 0. Then we run our number line. And I do negative 1. So f prime of negative 1 equals 15 times negative 1 squared times negative 1 squared plus 1. It's a positive, a positive, a positive, so it's increasing. And then f prime, that's plugging in negative 1. F prime of 1 equals 15, 1 squared times 1 squared plus 1, which is positive, 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 positive. So we have increasing the intervals of increase from negative infinity to 0 or 0 to infinity. Bless you. Then we have a point of inflection at 0 something. So we do f of 0 to get on the original. 15 and 0 to the 4 plus 15 times 0 squared. 0. Okay, what we're going to do is we're going to talk about the second derivative now. You do the exact same things as the first derivative, except where it's positive when you plug it into the number line, you get concave up. And where it's negative, you get concave down. That's the only difference that happens. Now, what the heck is concave up and concave down? If I give you a graph like this, these are mins and max. Everyone's really good with that, correct? That's not rocket science. This is decrease to the min, increase to the max, decrease to infinity. correct? Everyone's good with that. That makes sense to you. Concavity is where I lose people. Concavity happens at a point of inflection. That's where concavity change happens. And another place that a concavity change happens, directly in the middle of a max and a min. So this is concave up and this is concave down, and that's how people visualize it, as complete concave up and a complete concave down. But this is also concave up, and this is also concave down. You don't need the full arm. Okay? So in this particular graph here, this is going to be my point of inflection. The point of inflection is where your concavity changes. So a point of inflection can be like this, like we've talked about. And then this would be concave what? Visualize it. Don't tell me. Visualize it, and then pretend it keeps going. What is this? Concave what? Up, because if I kept going, it would look like that, right? And this is concave what? Down, because if I kept going, it would look like that. We agree? So that's a perfect point of inflection. This point of inflection will show up in your first derivative, and it'll show up as a critical number in your first derivative, and it'll show up as a critical number in your second derivative. That's when it's a plain old point of inflection where it does that curve. This type of point of inflection, where it happens between a max and a min, that does not show up in our first derivative, correct? As a critical number, because the critical numbers that would show up in our first derivative would be these red ones, the maxes and the mins. We agree? But it will show up as a critical number in our second derivative, where it changes concavity. So this here is concave what? Up. People will tell me, no, it's concave up to here. No, it's not. At the point of inflection, our concavity changes. So this is concave up till we hit here. Then what is this? Concave down. Do you see how it's not a full problem? So people get really stuck on this. I get this all the time. They tell me they're concave up to here. No, you're not. Wherever your point of inflection occurs, your critical number of your second derivative, this is where f prime double prime of x equals 0. Wherever that happens, concavity changes. Okay? That would be your point of inflection. So if I ask you just about concavity, do you need to find the first derivative and answer all the stuff about it? No, you'll need to find the first derivative, because to get the second derivative, I have to get the first, and then derive that to get the second. That's all you have to do about the first derivative. You don't have to answer any questions about the first derivative. Okay? So, we're going to talk about concavity. I'm going to give you this one. So we're going to use this one. F of x equals 2x cubed plus 9x squared plus 12x minus 4. I'm going to tell you right now that if it's a polynomial, concavity is really easy to find, because you're just doing power rule to keep getting your derivatives, correct? When it's other things like a rational, you're going to have to do quotient rule and then quotient rule again, right, to get them. So it's more advanced when it's like that. So enjoy the polynomials for a second. So if I want to know the concavity or the points of inflection, if they ask me that, the points of inflection, or they ask me for concavity, I immediately get to my second derivative. I don't care anything about the first one. Okay? I need to find it to get my second derivative, but I just find it and then move on. Don't answer any questions. So f prime of x equals 6x squared plus 18x plus 12. Now some people try and take a 6 out and break it down. No. You find your first derivative, you say thank you very much, first derivative, and you go and find your second. Okay? Because if you take that 6 out, you're now having to do product rule. We don't want to do that. So we're going to go f double prime of x, and we're going to get 12x plus 18. What can I take out? You take out a 6, and I'm left with 2x plus 3. And they can ask you for the critical numbers of the second derivative, correct? The critical numbers of the first derivative get you maximum, mins, and possibly a point of inflection. Yes? The critical numbers of the second derivative only get you a point of inflection. Now, sometimes people will get critical numbers and they're like, oh, it's for sure a point of inflection. Remember that your asymptotes come up as critical numbers as well, right? These are polynomials, you can't get asymptotes. But if it was a rational, we could. So, let's talk about critical numbers. Of f double prime. So we have 2x plus 3 equals 0. The 6 doesn't do anything. 2x equals negative 3. X equals negative 3 over 2. So I go and do my number line. I'll do it in the middle here. I'm from negative infinity to positive infinity because it's the cubic function and that's what they do. And then I have negative 3 halves here as my point of inflection. Now I know it's a point of inflection and not an asymptote. Why? Second derivative could still be an asymptote. Why do I know it's not an asymptote? What mathematical knowledge do I have walking into this class knowing this cannot be an asymptote? Yeah. It's a polynomial. Polynomials don't have asymptotes. They have a domain of negative infinity to positive infinity. They're correct. They're a continuous function. Correct? So I know that that has to be a point of inflection. So if I go f of negative 3 halves, I'm going to get 2 times negative 1.5 cubed plus 9 times negative 1.5 squared plus 12 times negative 1.5 minus 4. Negative 8.5. So that's our point of inflection, correct, on this graph? Now we need to find out if it's concave up or concave down on either side. How do we do that? Not increasing, decreasing, same steps though. Where f double prime of x is greater than 0, it is what? Nope. Totally different. This isn't f prime, this is f double prime. I have a title up there. Probably can give you a hint. Where f double prime is greater than 0, what do you think it is? Concave what? Up. And where f double prime of x is less than 0, what do you think it is? Concave down. So we're not going to run test points on the first derivative if they ask me for concavity, right? If they ask for concavity, I'm going to run right to the second derivative and do it. So I need to pick something less than negative 1.5. So I'm going to pick negative 2. So f double prime, negative 2 equals 6 bracket 2 times negative 2 plus 3. So the 6 is a positive. 2 times negative 2 is negative 4 plus 3 is a negative. What's a positive times a negative? A negative. So what's happening here? No. Second derivative, guys. Concave down. Increasing, decreasing doesn't happen on second derivative. That is first derivative. And that means we need to pick something bigger than negative 1.5, so I'm picking 0. If I get a choice of 0, I will choose it every day, all day long. So this is going to be positive, and then positive. So this is positive here. Second derivative is positive. So what is that? Not increasing. Concave up. So So this is concave down. From negative infinity to negative 3 over 2. And concave up from negative 3 over 2 to infinity. Okay. Why don't you guys try this one? Okay. This is what I want from example 2. All the brain matter. So we're going to use g of x equals 3x4 minus 16x cubed plus 24x squared. What I want are all these things. I want the domain. I want the critical numbers of the first derivative. I want intervals of increase, decrease. I want max mins. What else do you think I want? Critical numbers of the second derivative. Which give me what? Points of inflection. The critical numbers give you the points of inflection. From there, you can get the what? Yeah, intervals of concavity. Go. The domain. It's a polynomial, so it's negative infinity, positive infinity. Critical numbers of the first derivative. We need g prime of x equals 12x cubed minus 48x squared plus 48x. Then 0, we've set equal to 0. Take out a 12x, and we're left with x squared minus 4x plus 4, which breaks down into 12x, x minus 2 squared. So the critical numbers are x equals 0 and 2. Intervals of increase, decrease, we have to figure that out. We have negative infinity, we have 0, we have 2, we have infinity, and we have to plug in. So we do g prime of negative 1 is going to equal 12 times negative 1, and then negative 1 minus 2 squared. So that's going to end up with a positive times a negative times a positive, correct? Which results in a what? Positive times negative times a positive. Negative. And for this one, we have to plug in 1. So g prime of 1 equals 12 times 1 times 1 minus 2 squared. This one doesn't matter, it's always going to turn positive. So it's positive, 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 so it's positive. And then g of 3, g prime of 3, equals 12 times 3 minus 2 squared is a positive, 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 so it's going to be a positive. So here we are going from decreasing to increasing. I'll even draw it to help myself out. So I decrease to increase. So what's happening at 0? Minimum. And this one I'm increasing to increasing. So what's happening at 2? So we have a minimum at, I don't know, 0, and then we plug it in. That's not F. G of 0 is 0 because you plug it in and get 0. So we have minimum at 0, 0, and we have a point of inflection at g of 2. What's g of 2 equal to? 8? 16? How did I hear 8? 2 and 16. Okay, then we need the second derivative because we need the critical numbers of the second derivative. So g double prime of x, I do not use this. I'm going to have to do product rule if I use that, correct? That would suck. So go back to your original easier one and use that one. So g double prime will be 36 x squared minus 96 x plus 48. What can I take out? When I take out a 12, I'm left with 3x squared minus 8x plus 4. Then I have to do decomp, correct? So I get g double prime of x equals 12. If I want to do decomp on that, I go 3x squared minus 8x plus 4. What multiplies to give me 12 and adds to give me negative 8? Yeah, negative 6 and negative 2. Take out a 3x, you're left with x minus 2. Take out a negative 2, you're left with x minus 2. So I get x minus 2 and 3x minus 2. So my critical numbers of my second derivative are x equals 2 and 2/3. Now some people will say to me, but wait, I only had one point of inflection at 2. That's that true point of inflection. That's that one that just does that weird little S-curve through it, correct? The other one is a point of inflection of a changing concavity. So it's probably between like a max and a min or something like that, okay, or after a max and min. So our points of inflection are at g of 2, which we already discovered was 16, so 216. And then the other one is at g of 2/3. Did anyone find out what that is or why? Sorry? 176 over 27. Then we have to do a number line with our inflection changes. So we have 2/3 and then 2, negative infinity, positive infinity, and we have to plug in values into g double prime, so into this. So say I'm going to pick 0, 1, 3. Okay, I'll do it down here. I'll go g double prime of 0 equals 12 times 0 minus 2 times 3 times 0 minus 2. So it's going to be a positive, negative, negative, which makes it a positive. Then g double prime of 1, trying to do it where it's spaced. 12, 1 minus 2, and then 3 times 1 minus 2. So I'm going to get a positive, negative, positive. So this one is negative. And then g double prime of 3 equals 12 times 3 minus 2 times 3 times 3 minus 2. So your intervals of concavity, this is concave up, concave down.